So hi everyone, thank you for the introduction. My name is Orr, I'm from Yonadav's group in material engineering, and today I'm going to talk about correlated cathodoluminescence in self-assembled quantum dots. So our group is interested in materials with bright emission. Here is an example for a sample of polymer with our material, lead halide quantum dot perovskites that illuminate by UV. And here is just the polymer, and as you can see, it's quite bright. And we want to test if we can increase this emission. Here we're measuring cathodoluminescence, and I'm going to show here the first demonstration of superfluorescence triggered by free electrons, where in this case, if we take dispersed quantum dots, they emit light regularly, but if they are confined to a region that is much smaller than the wavelength, we're expecting to see a fast burst of and fast and intense burst of photons, which called superfluorescence. And I also going to show how we switch between these two regimes in cathodoluminescence. So first, the material that we're using, cesium lead bromide, is a perovskite. It has a perovskite lattice. It was first synthesized to colloidal quantum dots by Perovskite and her colleagues in 2015, and the result is these 10 nanometers cube. The emission is very sharp, around 515, and when this little quantum dot is excited, electron and hole are formed, and they are confined to this cube. And this little area, this little region, may increase the probability to recombine and to emit photon, and therefore the high photoluminescence quantum yield. And in general, this structure affect the optical properties in our material. So our sample, we make a sample by taking these quantum dots, mix them in polymer, and then spin coat it onto a substrate. Here you can see SEM micrography of our sample, and here the black background is the polymer, and the white spots are the superlattices of quantum dots. Now, if you go in higher magnification, you can see that these quantum dots are well defined, well separated. There is no fusing, and they are quite ordered. And it's happened for every superlattice here. It's very reproducible. And also, if we take cross-section of the sample, we can see that these superlattices are not thicker than 2 quantum dots across. And they form only at the top of the polymer or at the interface between the polymer and the substrate, as you can see here. So what we expect to see when we in these superlattices. So as I mentioned in the introduction, we have 2 regimes of emission that depends on how well the quantum dots are packed. So if they're dispersed, we expect emission that proportional to basically to probability for emission, and the emission rate is defined by the time T1 is defined by the emission rate. Now, if you take these quantum dots and put them together into small region, the state become multiple quantum dot states, and the transition matrix change accordingly. And the rate, the surprising thing, or what's come out from it, is that the emission rate increase by the factor of the quantum dot that participate in the emission. So experimentally, what we are expecting to see, emission rate increasement by factor of n, same for the intensity. We are also expecting to see a non-zero dipole moment, and another mechanism that causes coupling is the dipole-dipole interaction that shifts the energy, the emission energy in proportional to the dipole moment square over the distance between two emitters cube. So how do we test it? We have a cathodoluminescence, time-resolved cathodoluminescence setup. The electron gun is triggered by pulsed laser, and electron pulse, it results in an electron pulse that hit our sample, and we collect the light, collect and analyze the light that come out of the sample, and we made two realizations of this experiment. One, when the electron beam is focused to size smaller than a superlattices that hits few quantum dots, and the other is defocused electron beam, where the pulse, the electrons of the pulse are very far from each other. And now our results, we see that these two are quite different. The two emissions are quite different. The defocused beam creates this broad spectrum of emission, which is attributed to spontaneous emission, and the focused beam creates this very sharp and redshifted emission spectrum. Also, we see that the emission rate here is the intensities and the rate are 5 times more, are 5-fold higher for superfluorescence relative to spontaneous emission. And we also simulate this based on the properties of the quantum dots and the electron beam shape. And we have quite good fit to our theory. So this experiment took place during COVID time, and it was the tool is in some. We used the tool once in Switzerland and once in Paris. So we had to do some complementary optical measurement in the Technion, and we did this. We measured the spectrum in 4K in temperature of 10 Kelvin, and we see more or less the same feature. Interesting thing here is that we see both the superfluorescence and the spontaneous emission and the superfluorescence at the same time. Unlike the electron, when we need to do two different experiment realization to see each peak. So here, in the optical regime, we see them together. We see that the superfluorescence emission is polarized, unlike the spontaneous emission, which is pretty much what we expect. And another nice thing is that once we increase the intensity of the excitation, we see that the superfluorescent peak grows faster than the spontaneous emission peak. And it follows a cubic trend, square trend, where the spontaneous emission following linear trend. We also see growth here of the multi-exciton peak, which takes some of the energy from the spontaneous emission, and this is probably what caused the make it less linear at high powers. So our conclusion is that first, electron beam can, and we show it here experimentally, can trigger superfluorescence. And in the future, we want to test what are the limits for free electron superfluorescence. Can we, so we saw that we can go from here to here with maybe coupling 5 quantum dots. Can we go higher to more quantum dot to participate in the superfluorescence and to get higher enhancement? And also, can we go to the other limit and measure cathodoluminescence from single quantum dot? So this work could not happen without the following people: Yonadav, my supervisor, Ehud Schechter, that made all of the synthesis of the colloidal nanocrystal synthesis, Alina Nagel, that helped me a lot with the optical measurement, Alexei, that did the theory, and Ido, Alexei's supervisor, that both of them also helped me with designing some of the experiments. And thank you for your attention.